Have you ever seen the Richter scale number for an earthquake and wondered, what does that really mean? Or how we can even measure a quiet chat and a deafening rock concert on the very same scale? Well, the answer is a super powerful math tool that, let's be honest, can seem a little intimidating, the logarithm. But it's so much more than a chapter in a textbook. It's kind of like a secret language for making sense of our world. So, here's our game plan for this explainer. We're going to break it all down step by step. We'll start with what a logarithm even is, then we'll unlock their superpowers, see how to actually use them, point out some common mistakes to avoid, and then the big finale, why any of this actually matters in the real world. Ready? Let's jump in. All right, first things first. What in the world is a logarithm? The most important thing is to stop thinking of it as some new, complicated concept. Instead, just think of it as the other side of something you're already familiar with: exponents. And really, at its heart, the definition is that simple. A log function is just the inverse of an exponential one. They're like two sides of the same coin. They basically undo each other. Think of this slide as showing the same relationship, just in two different outfits. On the left, we've got the exponential form we all know and love. A base b to the power of x equals some number y. The logarithmic form on the right, it just shuffles that same info around to ask a question. It asks, hey, what power x do I need to put on this base b to get y?
Let's make this crystal clear with an easy example. We all know 2 cubed is 8. That's the exponential form, so the logarithmic form just asks the question, 2 to what power gives me 8? And of course, the answer is 3. So log base 2 of 8 equals 3. See that? It's the same three numbers, just a different point of view. So here's the key takeaway. A logarithm is an exponent.
Okay, now that we've got a handle on what a log is, let's get into its three main properties. I kind of like to think of these as superpowers because they let you break down and simplify expressions in some really amazing ways. And here is the whole secret to understanding these properties put perfectly by the math district. The reason these rules even work is just because logarithms are exponents. That's it. So all the log rules are really just exponent rules wearing a clever disguise. And this table just lays it all out beautifully. Look at the left side. Those are the exponent rules you probably learned a while ago. When you multiply things with the same base, you add the exponents. When you divide, you subtract the exponents. A power to a power, you multiply. Now, just glance over to the right. The log superpowers are a perfect mirror. The log of a product, it turns into a sum of logs. The log of a division, it becomes a subtraction. And a log of something to a power, you can just pull that power right out front. They're exactly the same logic. So how do we actually use these superpowers? Well, we mainly do two things. We either expand a single messy logarithm into several simpler ones, or we condense a bunch of logs back down into just one. Let's see it in action. Okay, let's start with a really simple expansion. We've got log base 5 of 2 times x. What's the operation happening inside? It's multiplication. So we grab our product rule superpower. That lets us split it into two separate logs that we add together. Log base 5 of 2 plus log base 5 of x. And that's it. You've expanded it. Simple as that. Now let's try going in the opposite direction. We want to squish this whole expression down into one single log. First up, we use the power rule, but backwards. We take those numbers out front and move them back up as exponents. So the 3 hops on top of the 4, and the 2 hops on top of the k. Now we have log of 64 minus log of k squared. And since we're subtracting two logs, we can use the quotient rule, again, in reverse, to combine them into one log of a fraction. And boom, log of 64 over k squared. Now, using these properties is awesome, but it's also really, really easy to fall into some common traps. So let's spend a minute on the biggest mistakes so you can steer clear of them. This one is, without a doubt, the number one mistake people make. The product rule is for the log of a product, something being multiplied, not the log of a sum. There's no fancy rule to simplify the log of m plus n. It's just stuck like that. Don't try to split it up. And here's another classic mix-up, this time with the power rule. That number r out front multiplies the entire logarithm. It does not become an exponent on the whole thing. The power rule only works for an exponent that's inside the log, on the argument itself. Okay, pop quiz time. Take a look at this expression. Which one of these is the correct way to expand it? A or B? I'll give you a second to think. Got an answer? The correct one is B. Did you get it? Here's why, and this trips a lot of people up. Both the K and the P are in the denominator.
They're both being divided. So when you expand, they both have to be subtracted. All right, so we've covered the what and the how, but that brings us to the biggest question of all. Why? Why do we even learn this stuff? Well, it turns out logarithms are hiding in plain sight, absolutely everywhere. I mean, seriously? From measuring earthquakes with the Richter scale and sound with the decibel scale, to calculating how your money grows with compound interest, measuring acidity in chemistry with the pH scale, and even figuring out how fast computer programs run, logarithms are the tool we use to wrap our heads around things that grow or shrink at insane rates. So let's circle back to earthquakes. The Richter scale is logarithmic, which means every time you go up one whole number, the actual ground shaking gets 10 times stronger. So a magnitude 7 quake isn't just a little bit worse than a 6, it's 10 times stronger, and it's 100 times stronger than a 5. Logarithms let us take these gigantic differences and put them on a scale that actually makes sense. And it's the exact same idea for sound. A 70 decibel vacuum cleaner isn't just a little louder than a 60 decibel conversation. The actual sound intensity is 10 times greater. Logarithms let us compress this enormous range of sound into a simple scale from, 0 to 120 that we can actually comprehend. So if there's one big thing to take away from all this, it's this. Logarithms are a special kind of language. They're the language science and technology uses to talk about things that exist on massive scales, from the quietest whisper to a jet engine, from a tiny tremor to a world-shattering earthquake. Ultimately, they're a tool for gaining perspective. They let us understand the true scale of the world all around us, which kind of makes you wonder, right? If they can help us make sense of something as powerful as earthquakes and sound, what other huge invisible forces in our universe could this mathematical language help us understand next?